Hi, I'm Samantha Corrado, and I'll present our study, Trajectory Clustering within the Terminal Airspace Utilizing a Weighted Distance Function. This work has been completed by myself, Dr. Tejas Piranik, Dr. Olivia Pinon-Fisher, and Professor Dimitri Mavros. I'll begin with a review of the introduction and some background for this work. Then I'll introduce our proposed method, explain our implementation of this method, and discuss the results we obtained, and finally I'll conclude the presentation. For the past 2 decades, many global efforts have been underway to modernize aviation systems. These efforts include NextGen in the US and Cesar in Europe. These efforts primarily focus on improving the efficiency, reliability, safety, sustainability, and cost-effectiveness of aircraft operations. Today, aircraft are equipped with numerous sensors to collect a large amount of data for each flight. This has led to the establishment of structured routine data collection and analysis programs such as the Flight Operational Quality Assurance, or FOQA program. Considering as well the advances in modern machine learning techniques, operational insights using data-driven techniques have been gaining significant momentum to improve aviation safety and efficiency. To support the modernization efforts' goals of improving the safety and efficiency of the airspace system, high-precision trajectory prediction and robust trajectory anomaly detection methods are necessary. Developing methods to apply within the terminal airspace is most often the focus due to the terminal airspace operations' high impact on both individual flight level and system level safety and efficiency. The tasks of trajectory prediction and anomaly detection are very complex within the terminal airspace because within the terminal airspace there's a higher traffic density, interdependent utilization of both airport and airspace resources, and more complex traffic dynamics because it's a more constrained airspace. Due to this, in-depth analysis of the complex terminal airspace trajectory operations are required. Trajectories that follow a similar spatial path, or those belonging to the same air traffic flow, tend to correspond to a specific structured operation within the terminal airspace as defined by air traffic control. On the right, different air traffic flows are represented by the different colors. For each of the structured operations, the approach and climb paths mandated by air traffic control typically have very distinct characteristics, specifically in terms of their energy profiles. And this can be visualized by looking at the specific energy profile of flights arriving at an airport, where displayed in the image on the left is the interquartile range of specific energy for each flow within the last 15 nautical miles of flight. It's evident that for each of the different flows, different specific energy profiles are anticipated, and these profiles are certainly distinct. When algorithms to detect anomalies and predict trajectory paths are not provided the additional operational or spatial context related to the air traffic flows within the airspace, the algorithms may yield more conservative results, such that anomalous trajectories are missed by the algorithms, or the algorithms are not able to provide very precise trajectory predictions. For instance, consider the trajectory in pink, meaning that spatially it belongs to flow B. This trajectory is clearly an anomaly with respect to flow B. However, without being provided the additional context that the trajectory spatially belonged to flow B, this anomalous trajectory may remain undetected since the energy profile is exactly within the range of flow A. Therefore, precise air traffic flow identification is necessary to enable the success of trajectory prediction and trajectory anomaly detection efforts within the terminal airspace. Air traffic flows are typically identified using clustering algorithms. Generally, this is an unsupervised machine learning problem, as ground truth is not readily available. Clustering is a task of dividing the population of data points into a number of groups such that the data points in the same group are more similar to other data points in the same group than those in other groups. In aviation literature, algorithms such as k-means, spectral clustering, DBscan, and HDBscan are most often used to perform the trajectory identification task. Clustering algorithms determine the partitioning of the airspace into flows according to some distance function. One of the most critical components of trajectory clustering is the definition of appropriate distance function. The standard Euclidean distance is the most often utilized distance function within the aviation literature. However, a unique property within the terminal airspace is that it experiences a very high density of aircraft that are either converging to or diverging from the airport location. This results in the distance between trajectory points closest to the airport location being very small, even for trajectories not in the same flow, And also, the distance may be relatively large when trajectories first enter the airspace at the border of the airspace, even for trajectories within the same flow. For instance, it is evident that the distance between trajectory points when entering the airspace for the yellow flow are very large, whereas this may not be the case for flows such as a light blue flow or orange flow. Therefore, using the standard Euclidean distance function may skew the classification of trajectories, which can result in the misclassification of trajectories or a less precise clustering. Further, it's been noted in some studies that using a standard Euclidean distance is inadequate for some applications. Some other distances have, however, been proposed. These include the symmetrized segment path distance. This SSPD distance has been demonstrated to more precisely identify air traffic flows, but there's a significant trade-off between computation time and accuracy, where computation time is very important in clustering because we want our clustering to run efficiently. Additionally, two studies have proposed individual point-based clustering methods relying more on iterative clustering and dependency trees. However, entire trajectory records are not clustered at once in these methods, which limits the applicability to in-time or real-time frameworks. Overall, a computation time-efficient distance function that mitigates the effects of converging and diverging trajectories is required. Provided two n-dimensional trajectory vectors Ti and Tj with x and y coordinates, the Euclidean distance computation proceeds as the square of the sums of the distances between all trajectory points. Very standard computation. However, provided the same two trajectory vectors, let's now consider a weighted Euclidean distance function. The weighted distance introduces an additional trajectory point weighting term, which is essentially an importance factor to be assigned to each point, where the importance factor may be determined according to the relative location in the sequence of trajectory points, which is important since we mentioned the issue of the distances being very small closest to the airport location and distances being disproportionately large furthest from the airport location. So for instance, consider these two plots of latitude versus longitude. It's possible to create a weighting function that weights the points closest to the airport location and closest to the border of the airspace less than those in the center of the trajectory sequence. Therefore, a weighted Euclidean distance function may enable mitigation of the effects of converging or diverging trajectories compared to the standard Euclidean distance function, such that classification may be less skewed and instead more precise. HDBscan, a hierarchical density-based clustering algorithm, is selected to test the effectiveness of the proposed weighted distance. The HDBscan algorithm extends DBscan by converting it to a hierarchical clustering algorithm where a flat clustering is ultimately extracted based in the stability of the identified clusters. HDBscan has the ability to identify clusters of varying densities, which is very important because, for instance, the pink and yellow flows are certainly much less dense than the very tight purple, blue, and orange flows, so we want an algorithm that can handle varying densities. And also, HDBscan utilization has increased its prevalence in aviation literature recently. The algorithm requires only a single input parameter related to minimum cluster size. And additionally, an optional smoothing input parameter exists, which controls how conservative the clustering is. And this is a larger value for the smoothing parameter, means that more points are going to be declared as outliers, and the clusters are going to be restricted to more dense areas. So, HDBscan is applied to determine whether air traffic flows are identified more precisely utilizing a weighted Euclidean distance versus the standard Euclidean distance. The primary data source is OpenSky Network, where state vectors were extracted using the Python traffic library. A sample of the data extracted relevant to the study is displayed on the right. We have the call sign, time, latitude, longitude, and baro altitude. Additionally, ASOS data was extracted. ASOS stations take minute-by-minute observations and generate basic weather reports. Access to the processed weather reports is provided by the Iowa Environmental Mesonet. A sample of the information extracted can be seen on the right. Specifically, the mean sea level pressure column is important to this work in computing a height above ground level because it enables a correction of the airport altitude to barometric altitude. I'll now present the data processing steps in detail. The first step involves data extraction and fusion, where open sky network data is requested for a specific terminal area, state vectors that are redundant, contain empty values, or our general aviation flights are discarded, then the ASOS data is fused based on timestamps. Next, specific flight segments are identified by first separating them into individual flight segments and then determining whether the segment is a departure or arrival. Then, identifying the state vector that can be said to be associated with touchdown or liftoff points is performed. Then, the data augmentation takes place, in which the lowest flight segment altitude is determined such that the height above ground level for each state vector may be computed, where flight segments that do not reach below 100 feet above ground level are discarded because we don't have enough data for them to arrive at the airport location. And finally, a cumulative ground track distance for each state vector is computed. Finally, the feature vectors are generated where only state vectors within a 20 nautical mile radius are kept, and then the flight segment's latitude and longitude values are resampled on 50 uniformly spaced intervals between a cumulative ground track distance of 0 and the maximum cumulative ground track distance for that flight segment. These values are then projected to a UTM coordinate system where the Cartesian coordinates are finally stacked to produce the feature vector for clustering. Flights arriving at San Francisco International Airport throughout all of 2019 were considered. About 180,000 arriving flight segments were extracted and identified. These flights are both domestic and international. 187 airlines are represented in the data set, where the majority of flights are flown on United Airlines. And 110 different aircraft types were identified, with the majority of flights being on A320 aircraft. The total data set was separated into daily and weekly data sets for clustering on those timescales. From the total data set, 237 days are extracted, where each day contains about 500 trajectories each. And then 30 weeks were extracted, where each week contains about 3,500 trajectories each. The HDBscan algorithm requires a minimum cluster size input parameter. So in this study, the minimum cluster size parameter is set to 2% of the number of trajectories in the dataset being clustered, either one of the daily datasets or one of the weekly datasets. However, there may be bias in the results related to the percentage of outliers identified, and this must be addressed. So the smoothing parameter introduced earlier is adjusted iteratively until the clustering for the dataset produces within 10 to 15% outliers, and then the loop will exit. There were 4 weighting schemes implemented in addition to the Euclidean distance. The shape of these weighting functions were inspired by the shapes of beta and normal distribution, probability density, and cumulative distribution functions. The 4 weighting schemes are displayed below for reference. To test the robustness of our method, we include weighting 2, which weights trajectory points in the center of the sequence very, very high, yet the majority of the other points are weighted near 0 at both ends of the trajectory sequence. We expect this weighting scheme should lead to a less precise clustering due to the focus on a limited segment of the trajectory points. Point 0 is at the airport location, and point 50 is the point entering the airspace. To evaluate and compare the results, it's considered that if air traffic flows are more precisely identified, then it should follow that the distances between trajectories within a flow and the flow centroid will be minimized. To provide an example of the distance between a trajectory and its flow centroid, consider this flow. The centroid is represented by the dotted line, and the trajectory in the flow that's considered is a solid pink line. At any specified point along the trajectory, the distance between the trajectory and its centroid may be computed. Then, the distance computed at all trajectory points is averaged to obtain the distance between the trajectory within a flow and its flow centroid. Therefore, to evaluate results for each day or week, the mean distance between trajectories within a flow and the flow centroid is computed for the Euclidean distance clustering and the different weighting scheme clusterings to enable a comparison. Additionally, graphic representations of specific days or weeks enables visual inspection to support the results. Looking at the daily results of all 237 days combined, the top plot is all the weighting schemes that were implemented for reference, and the bottom bar chart displays the percentage of time or percentage of days that the mean distance between trajectories within a flow and the flow centroid for all flights within the dataset is lower for the specified weighting scheme than the value computed for the Euclidean distance. A horizontal line is drawn at 50%, and we want these bars to be above 50%, except for weighting scheme 2. Then, On the right, the ratio of the Euclidean distance to the weighting scheme is displayed such that the magnitude of the performance can be assessed. In this case, if the ratio is above 1, then the weighting scheme performs better, as the mean distance between trajectories within a flow and the flow centroid for all flights within that day is less than that using the Euclidean distance. It's evident that weighting schemes 1, 3, and 4 outperform the standard Euclidean distance as expected, and weighting 2 does not perform as well as the other, again testing the robustness of our method. Next, we'll take a look at an individual day clustered to the Euclidean distance compared with weighting 1, for instance. June 10, 2019 was selected. At first glance, these two clusterings look relatively similar. However, it can be seen that for the purple flow, there's a trajectory that's way off the nominal track of the other trajectories in this flow that the Euclidean distance does not identify as an outlier, but weighting 1 does. Additionally, there are some blue trajectories that appear to be visually outlined that the Euclidean distance does not pick up, but weighting 1 does, making the blue flow a tighter flow. And similarly, there are some outliers in the pink flow that the Euclidean distance does not pick up, but weighting 1 does, and making the pink flow a tighter flow. Overall, it appears that the flows identified with weighting 1 when compared to the Euclidean distance are tighter or more precise, which is what we were hoping for. And also what we were expecting based on the quantitative results on the previous slide. Some of these flows can now be looked at in some more detail. This is the blue flow mentioned previously, where it is evident that there are a couple of outliers that are off the normal flow path that the Euclidean distance does not identify. These outliers are represented by black lines in the Euclidean distance chart. Again, we see the blue flow is tighter as we expect. We see the darker blue in the center as the main trajectory path, kind of where all those trajectories overlap. Since the opacity of the plot is less, we can see where the primary flow path is. And we can see that those two black flows are definitely not aligning with it, which the Euclidean distance is not able to pick up, but weighting 1 is, making the flow tighter. Then, in the pink flow, weighting 1 also has a very clear improvement where the solid black lines and the Euclidean distance clustering flow do not conform as tightly as they should. Again, we can see from the opacity, the saturation of the standard flow path, we see that these black lines are very much so off, especially the one on the right is sort of really going around all the other flows in this flow. So overall, it's evident that there is visually a more precise identification of flows where the outliers are more robustly identified with weighting 1. Weekly clustering results are also presented for different weighting schemes. It's clear that the results are very similar to daily clustering results, such that the performance is generally improved with the selection of an appropriate weighting function. So it can be stated that the time scale of clustering is not biasing the results. Weighting 4 does perform a little bit less good as it did previously. However, it still is not performing worse, and it does stress the importance of selecting an appropriate weighting scheme. So now, to conclude, we've demonstrated that a weighted distance function shows a lot of promise in improving air traffic flow identification computed with the Euclidean distance for both daily and weekly data sets. Computation time was not significantly increased, if at all. We used the HDBscan library based in the sklearn algorithms, and we just used the Euclidean distance metric and also their standardized Euclidean distance metric to effectively implement a weighting scheme, and the computation time difference was insignificant if there was any at all. They clustered in seconds. It appears that more precise or tighter flows are identified when we actually look at the plots of the flows. And finally, there appears to be a more robust identification of outliers by the HDBscan algorithm when we go and look at the flows. It's noted that the selection of an appropriate weighting scheme is very important because not all weighting schemes perform better, such as weighting 2, which performed worse, which was anticipated, so again, indicating the robustness of our method and that we can't just throw any weighting scheme on there. It needs to be appropriate for the terminal airspace. So then we plan to extend this work by applying the method to other terminal airspaces with different runway configurations to assess the impact of runway configuration on an optimal weighting scheme. And also we want to apply the method to departure flights to evaluate the results, see if they're similar, and we see a similar improvement. And also something we want to do is investigate how the utilization of a weighted Euclidean distance may impact the results of a downstream anomaly detection method versus using the standard Euclidean distance. So how does a more precise identification of flows impact an anomaly detection algorithm downstream? So these are our primary references for this presentation, and thank you so much for watching.